Thanks very much. Great to be here. So I'm going to talk today about how we can sort of use some of the latest developments in machine learning and AI to try to, hopefully in the end, actually improve reproducibility. So people have long wanted to know what's going on inside the human's head. Back before we had MRI, people would come up with things like the robot phrenologist, which I don't think worked very well. But when fMRI was developed, invented, whatever you want to say, in the early 1990s, we suddenly had a tool that we could use to look inside a person's head without feeling bumps or cutting them open. And that led people to want to sort of make inferences about what a person's thinking about based on brain activity. And so early in the days of neuroimaging, we started seeing people, writing in their methods section, well, we saw activity in a certain area, and that means that we saw activity in the amygdala, that means the person must have been experiencing fear. And so many of us, long ago got concerned about what we called this sort of informal reverse inference. I wrote a paper about it back in 2006. And, what we realized was one of the goals that we should have is actually being able to use models to provide a real way to sort of infer, something about cognitive processes or contents from imaging data. And early on, people like Jim Haxby started developing methods to actually do this. So in his well-known 2001 paper, he showed that you could, take some data from a person looking at a bunch of different classes of images, and then based on other imaging data from that person, actually predict with pretty good accuracy what class of objects the person was looking at. And this set of tools has really exploded in its use. This is a PubMed search for fMRI and decoding or machine learning or deep learning, and you can see that it's, it's sort of exponential over the last decade in the use of these methods. But as somebody who's, thinks a lot about reproducibility, there's a lot of concerns to be had. And I think the best paper on this issue is this paper from a few years ago by Guy Alvaraqua called Cross-Validation Failure. So the first thing that he pointed out is that, when you look across the literature of people doing decoding, most of the sample sizes are small. Many of them less than 50, most of them less than 150. And what that leads to is a high degree of variability in the predictive accuracies. So he did some analyses showing on the right, you can see these are kind of various ways of estimating what's the kind of the sampling variability in predictive accuracies, and you can see you get sort of plus or minus 18 to 20% with fMRI. They separately compared like public versus private scores in a Kaggle competition, and there you see about 14, 15%. So this says that there's pretty big confidence bounds on the accuracy, the predictive accuracy numbers that we see in the literature. Now, this is additionally concerning when you look at how sample size relates to predictive accuracy. And what he saw was that across a bunch of different outcomes, basically accuracy goes down as a function of sample size. Now, why does that happen? We think that happens as a combination of the sampling variability due to small samples. So it's easy to get kind of a spuriously really large accuracy value if your sample's small. It's a lot harder to get it when your sample's big. And then you have some degree of publication bias and probably some degree of kind of trying lots of different methods and taking the one that gives the best result, what we would call probably accuracy hacking, so on analogy to p-hacking. And so what that means is that we have to be concerned about the degree to which we can actually believe, especially from small samples, predictive accuracy results. So the question is, is there a way to improve fMRI decoding with smaller samples, realizing that often we're not going to have huge samples. People can't often afford to go collect huge samples. So and one of the questions we're going to ask is whether we can leverage existing large data sets to get at that. And so many of you may have heard of this concept of foundation models. You've all heard of actual foundation models like GPT-3, GPT-4, BAR, DALI. And so my colleagues at Stanford, this Bonamassani paper, kind of laid out the idea of what is a foundation model. It's basically a model that's been trained on huge data, like internet scale data, generally using some kind of self-supervised learning technique, which means you don't need labeled data. You just take the data and allow the model to kind of predict the next thing or fill in part of the data. And then once you've trained it on that self-supervised objective, you can then apply it to many different tasks. So, you can go on ChatGPT and do all sorts of things that it was just trained to like predict the next word. But nonetheless, you can ask it to do lots of things that it can end up doing for various reasons. You can also train these models to go be sort of specialized once they've been sort of generally trained. That's what we call adaptation. That's what we're going to be doing here. So we wanted to ask whether we could leverage large shared fMRI data sets to create a foundation model. And the person who primarily did this work is Armin Thomas. He's a Stanford data science scholar and is on the job market this coming year if anybody is interested in having somebody around who does this stuff. He's great. This is work with Chris Ray in our computer science department. Armin presented it at NeurIPS last year, and all of the code and the pre-trained models and everything are in his GitHub repo if you want to play around with it. So the data set that we're going to leverage for pre-training is the OpenNeuro data set. Some of you may have heard of OpenNeuro. It's a large open database for sharing of a broad range of neuroimaging data types. I should mention that actually so OpenNeuro grew out of an earlier project called OpenFMRI, which was actually funded initially by CRCNS. So it had its birth in this program about a decade ago, actually more than a decade ago. And it's now one of the Brain Initiative data archives. There's a number of different ones. We're the one for a number of types of imaging data. The idea behind OpenNeuro is we can share any data set that follows a particular standard, the standard called the Brain Imaging Data Structure, or BID. So any data set, be it fMRI, MEG, EEG, intracranial data, now FNIRS, those data can all be uploaded. And they're all shared very openly using what's called a CC0, or kind of a public domain dedication. On the right, you see the growth of the database over the last 6 years. We started this in OpenFMRI had been started back around, I think it launched in 2013 or so. OpenNeuro launched in 2017, and you can see it's been basically constant growth, both in the number of data sets and the number of individuals. We now have over 35,000 individuals, almost all humans, but a growing number of rodents and other species as well. And mostly MR, but a growing amount of EEG, MEG, and other data types. So I mentioned that these data aren't labeled for the most part, or if they are, not very richly. And so the question is, how can we actually train a foundation model? How do you do self-supervised learning with fMRI data? So what I want to do is kind of step back a bit and talk about how you do it in language modeling. And I'll talk about we actually use 4 different approaches. I'm going to talk about 2 of them, kind of skipping over the others because I think it's not as important. So how do you do this with a language model? Let's say you want to train on Wikipedia. You have a sentence from Wikipedia. This is a shoe. And so the first thing you do is you embed those words into some multidimensional space. So you basically turn it from a set of words into basically a matrix, a set of numbers representing each word. And that can vary in its dimensionality. You can do it in various ways. One of the methods that we try is this thing called sequence-to-sequence autoencoding. And this is not as cool these days, but it's still, now that transformers are around, but it's still actually used particularly for sort of translation type things. So the idea here is you build a recurrent neural network, sort of takes the data, takes that embedding, encodes it into a lower dimensional space. So the idea is you're sort of passing it through a bottleneck, and then you decode it, and the idea is you want to reconstruct the entire sequence having passed it through that bottleneck. And then, so that's one of the methods we're going to use. And I'll say more about how we actually sort of test it. The other is what I'm going to call causal language modeling. This is basically the method that's used to train things like GPT-3 and GPT-4. Here the idea is you basically mask out, so you have like this is A, and you mask out the last word. And the idea is you want to have it predict the next word. So we're going to run it through this thing. The architecture is called a transformer. I'm not going to go into much detail about that. And the idea is you want to ask how well can it predict the next word. So it's just going to predict that thing, and we're going to ask how accurate are you in terms of that embedding. I mentioned we did 4 architectures. There's another kind of older transformer architecture called BERT. We tried a couple versions of that. It kind of falls in between these other 2, so I'm not going to go into any detail about it. But this is sort of the architecture. I'm going to walk you through a few of the steps. The idea is we start with an fMRI time series. We're going to basically we're going to put it into a lower dimensional space just sort of based on anatomy, and then do some stuff with it. And then ultimately on the other end, it's going to be either predicting the entire time series or predicting the next time point. So how do we adapt these things to neuroimaging data? Well, the first thing we want to do is we're not going to work with kind of voxel, hundreds of thousands of voxels, because we know that there's a lot of, we've already seen in a number of the talks today, yesterday and today, there's a lot of structure in the data. So we're going to reduce the data using what we call a parcellation. And there's a bunch of these different parcellations that are all based on taking lots of data and asking what's the kind of the generic structure that most people share. We're going to use one called DiFumo, and I'll just mention that what we're doing here is similar to the way that words are embedded into kind of a multidimensional space. We'll use this thing called DiFumo from Varaqua and others, which is based on a dictionary learning approach, and there's various dimensionalities. We're going to use the 1024 dimensional parcellation. It's a relatively sparse but soft parcellation, so the idea is you take a weighted average over the whole brain based on each of these 1024 networks. And most of them look like kind of little blobs or sets of blobs. So we take 200,000 dimensional data, run them through the parcellation to get 1024 dimensional data. And now we're going to apply these two models. So in the causal sequence modeling, we'll call it now, approach, we'll mask out the next time point in the fMRI time series, run it through this transformer, try to predict the next time point, and then back propagate the error to basically learn, to train the transformer to actually do that prediction task. So just based on that last time point. The sequence-to-sequence autoencoding is very similar. We train a recurrent neural network to take in that entire 1024 by however many time points we have, run it through this bottleneck, this low-dimensional representation, and then again now try to reconstruct the entire time series, and again compute the error on that and backpropagate that error and use that to train the network. So with the training data, we didn't use all of OpenNeuro. The data needed to be sort of pre-processed in the same way, and we don't yet have all of OpenNeuro pre-processed in the same way. I'll tell you a bit about how we pre-processed it in a moment, but we used over 11,000, almost 12,000 fMRI runs from about 1,700 people across 34 data sets. And this is a kind of a plot of the number of individuals. Where's my, not what I want. Sorry, I can't get my laser pointer. Anyway, this is the number of individuals, and this is the amount of data per person. So some of the data sets have a ton of data per person. Others have more people, less data per person. And they're basically all sorts of different data sets. I'm happy to say more about what went into them, but they really run the gamut from, image, like Bold 5000, which is basically people looking at a bunch of images, to individual brain charting, which has people doing like tens of different tasks. So the idea is not to train it to decode what task a person's doing. It's really to learn, what do fMRI data look like? How do they move in time, regardless of what the person's doing? They could also just be resting or watching a movie. We pre-process, as you know, fMRI data requires a lot of pre-processing. We run it through a tool that we've developed called fMRI Prep, which is a pretty robust pre-processing tool for lots of different data sets. We then take those data, which are on the order of, say, 200,000 voxels. We project them through the parcellation to get out 1,024 time series. And we hold out about 5% of the data for final evaluation with a minimum of 2 runs per data set. Now, one of the tricks is that the time points aren't aligned between data sets, right? So different data sets will have different temporal resolution. One might be 700 milliseconds, one might be 2.5 seconds. And we need to align those. So one of the things that's done already in large language models is something that's called a positional encoding, where you basically tell it, this is the first word, this is the second, this is the third, this is the fourth. We do, in addition to a positional encoding, we also do something we call a TR embedding. TR stands for repetition time, which is basically the time between, when the pictures are taken. So we basically, Armin came up with a way to embed information about the timing of when things are being acquired so that you can basically map between data sets that have different temporal resolutions without having to do any sort of interpolation. You're basically just telling it when was each of these time points acquired. And that's given to the model along with the positional encoding that says this is the first time point, this is the second, this is the third. Okay, so we train the model. The model's learn to perform. This is showing the training loss is the dotted line, and you would hope it gets better with training. This is the in-sample error. Both models get better. The evaluation loss is in solid. The reason that it's so much worse on the autoencoder is because we do something called teacher forcing, where we're actually giving it the right, rather than letting it give us the wrong answer and then feeding that back in for the next time step. We take its answer, but then we actually give the correct answer for the next time step. So the losses aren't really comparable. You can see for the causal sequence model, it overfits later in training such that the in-sample fit is much better than the out-of-sample fit, but it is learning, getting better. I'm not going to go into the details about how we determined the architecture. I think the main thing to say is that what we found was that Armin did a ton of hyperparameter examination. In general, what we found for both the autoencoder and the transformers was that higher dimensional embedding basically resulted in better performance. More layers generally didn't. So the transformer ended up having 2 transformer layers, and I think the autoencoder was 3 or 4. I can't remember the number there, but it was we basically kept it to a smaller number of layers with larger embeddings. Okay, so we've got our trained model now. It can predict the next time point. Now, how do we do decoding with it? So first, what data are we using? So we're going to use 2 data sets that were not included in the training data. One is the Human Connectome Project, which we took 100 people, unrelated individuals, doing 7 different tasks that we chopped up into 20 different, what we call mental states. And then we also have this multi-domain task battery data set that we've used before for other analyses that has each person with 16 runs doing 26 different tasks, and we treat each of those as a different mental state. That's a much broader set of tasks than the Human Connectome Project. In each case, what we're going to do is for each person ask, can we predict which of those 20 things or which of those 26 things are they doing based on a snippet of fMRI data collected during the block when they were doing that thing. So the idea is we train the model just on predicting the next time point, and then we're going to adapt it to doing this mental state decoding. How do we do that? Basically, we add what's called a decoding head. So we take the pre-trained model. It gives us out basically its encoding of the data. And then we basically just put a multi-layer perceptron on top of that, just a small neural network that learns to map from that encoding into one of 20 or 26 different mental states. And we just train now to maximize the probability of giving us the correct mental state. So we get a probability for each one. We do a softmax over that to get its decision. And we just want to maximize the probability of getting the right thing during training. Then we're going to ask what happens when we give it some data it hasn't seen before. We also wanted to do just kind of a baseline linear decoder. So what we do here is we take the data in, and then we just basically do a couple of linear steps. We do an aggregation over time, and then an aggregation over networks to give us, again, a probability. So it's like a couple of sort of like perceptron layers just put on top of each other. But again, just trying to, without using all the machinery of an autoencoder or a transformer, how well can we predict which of those tasks the person's doing, which is meant to mimic the usual kind of linear classifiers that people might apply to imaging data. So here are the data. So what we did was we varied the number of training subjects, because the idea is, can we actually improve performance with a very small amount of training data? And you can see for the linear baseline, we actually do, I think there's enough data per person that even with like one subject, you can sort of do reasonably well at predicting from other subjects. Not super well, but well above chance. That's the blue line here. And you can see that that's true both on, we're actually much better on the multi-domain task battery because you have a lot more data per task there. But you can see that we do substantially better using both the autoencoder and the causal sequence model approach. They asymptote not perfectly, but they actually do, they asymptote much better than the linear model. And the causal sequence model ends up in general doing a little bit better than the autoencoder, though both do substantially better than the linear model. So what this says is that we actually have hope that by instead of starting basically de novo, by starting with a model that's developed useful representations of fMRI data and how it changes over time, we can actually greatly improve our ability to then use those existing representations to make predictions about what's happening, what cognitive task is being performed, even though the pre-trained model was never trained to actually do that. We can look at also at what the support in the brain is for this, and we do this by what we call a feature ablation analysis, where we have those 1,024 different networks, the kind of sets of regions that come from the parcellation. What we do is we go in and basically put in each one, replace its data with sort of Gaussian noise, and then do that for all 1,024. Each of them has a loading on each voxel in the brain. And then we can ask basically what's the impact of, across all the different networks that contain that particular voxel, what's the impact of putting Gaussian noise into that voxel on the ultimate predictive accuracy. And what you can see is that they both, for both the autoencoder and the causal sequence model, I mean, the first thing is this is just a good reality check, right? It's pulling out features that make sense, right? Mostly kind of, somatosensory and motor and visual features. The one thing that you see is that the causal sequence model seems to, we haven't done kind of formal analyses on that, but it does seem to take advantage of a broader set of features. The autoencoder seems to be kind of more focused on kind of more primary sensory and motor areas, whereas the causal sequence model seems to take advantage of more voxels across the brain. Again, that hasn't been kind of directly established. Okay, so summary, we think that tools that have been developed from natural language processing, architectures for learning from natural language processing seem to actually be really useful for learning the structure of fMRI time series and then ultimately letting us make predictions about what's going on, by adapting those models to the decoding of mental states. And this causal sequence model, the sort of GPT-3 objective, seems to be the best one. And I mentioned the BERT objective seems to kind of fall at or below where that seek-to-seek model was. Better than linear, but not as good as the others. Though I want to mention one sort of final bit of work going forward. So one thing that we're really interested in is how to sort of extend this into thinking not just about like single processing streams, but actually thinking about what we call the multiverse of data analyses, right? We know from work that Tom led in the NARPS project that you can see substantial differences across processing and analysis pipelines in fMRI. And one idea to address that is to run data sets through lots of different pipelines and then look at how consistent the results are. Rasko Sirik in my group has been looking at a different approach that uses neural networks to build what we call a differentiable analysis pipeline. This is something people have been doing in other fields for the last couple of years, where you take he's been interested in connectivity analysis. So the idea is there's a bunch of steps in that analysis, right? Parcellation, time series estimation, filtering, connectivity estimation, and so on. You build each one of those as a differentiable node in a neural network. Okay, so that means that you can backpropagate error across the thing, and then you can do gradient descent and basically learn for some objective. Let's say it's task decoding or some age decoding, whatever the objective may be that you want to maximize. You can basically find you can do gradient descent and kind of find at least a local minimum of a particular set of parameters across those different processing operations that will give you the optimal predictive performance out of sample on whatever that objective is that you're trying to achieve. He presented sort of first versions of this at the ML for Health meeting last year. Still working on it, so it's not working yet, but I think if we can ultimately kind of marry this sort of stuff with the self-supervision stuff, I think that it could be a way to try to, again, make the outputs more robust to any particular way of processing data. Okay, so just want to thank you all, thank all the folks who've supported us, and Thanks.
Okay, thank you very much, Russ, for being on time. Any questions? Yeah.
Thank you for the great talk. So I'm wondering, this foundation model you talk about, would that benefit from, when you train the model, you talk about using different kind of data set, different subject, would that benefit from, training a model, training data set with a multimodality, and then you still embed, the data, looking at the low dimensional space, and then predict single modality? Would that be beneficial, train on multimodality?
It's an open question. Yeah, it's probably going to be harder, but yeah, we don't know.
Thank you. Any other questions? We'll do it.
Well, thank you for the talk. Great talk. So I was wondering if you have this foundation model as well. It goes a little bit similar to the question earlier, maybe, whether you show that you have some mental state decoding capacity, but I wonder if you have also looked at, presumably you would see some language network or even early visual retinopathy predictability, right? Have you looked at this more in depth?
Yeah, that's a great question. We've not yet tested it on that kind of between subject, biomarker prediction type stuff. In part, I would not feel comfortable doing that with the size of data that we have. I mean, I think biobank size data we could try it with, and that's something that's on the list to do. But we haven't had big enough data sets around it where we felt comfortable doing it yet. I mean, I think even Human Connectome Project, the full data set, if we did 1,000 subjects and we're trying to predict, cognitive ability or something like that, or ABCD, those are levels of sample size where I would feel comfortable to start doing that. But it's not something we've been able to do yet.
Sort of a great talk again. Sort of a follow-up, and it's a very naive question. So what are brain states? What is it that you're actually getting? Are brain states those cognitive?
I think that's a great question. I think about it as a distribution of activity over those 1,024 networks. So what's differentiating doing a motor task versus doing a theory of mind task? It's you take brain activity at a particular point in time, or in this case, it would be averaged across or combined across the run, not necessarily averaged, like a weighted average across the entire snippet of data. And it's basically going to be just what's the distribution of activity across those 1,024 brain networks.
Thanks. Really fascinating work, I think. I wanted to ask if, similar to large language models, where they can be fine-tuned, do you think these models could be fine-tuned to individual brains? If you took an individual brain and ran that data, would you be better able to predict its future states?
I think that's a great question. We've not yet tried that. I mean, there's two ways. You can imagine doing it either actually training it on the person, or you can do an in-context learning thing some of the models do now, and both of those are kind of interesting ways to think about fine-tuning. And Armin's currently working on another approach that actually tries to learn the parcellation as well, and that's somewhere where you can imagine individuals probably differ in their parcellations, right? This is a group parcellation, so it almost certainly doesn't fit any individual perfectly. And so learning the parcellation is one step towards that potential fine-tuning to an individual. Yeah.
Okay, last question.
Sorry, I'm going back to the previous question as well. I'm also interested about these mental states. So are you saying that these mental states are basically some form of embeddings or latent space, which we cannot really make sense of them, or we cannot make an interpretation of them by looking at the data? Or can we?
Yeah, I think it's an open question right now, and we've not done, other than the feature ablation analysis, we have not done deeper analyses to see, for example, if you look at what's the particular set of states that differentiate task A from task B, you would hope that if I compare like a theory of mind task to a motor task, I will see activity, I'll see relevance of voxels in areas that are known to be involved in motor stuff versus theory of mind stuff. We have not done those analyses yet. This is not meant to say that, this is a signal of what the task is. I'm not meaning to say that mental states just are embeddings. I'm meaning to say that you can decode mental states based on embeddings. And I would hope that that comes through. And the ablation analysis overall, at least, makes you think that it's pulling out sort of relevant areas, but we don't know yet. Yeah.
Thank you. Thank you, Russ.